All right, everybody, what we are looking at today is section 14.1 in our book. It is the locus. And right now, it's generally just going to be a bit of a new vocab word. Some of the stuff that we've seen already are going to be included, but then we're going to take it to a kind of a higher level like we've done throughout the year. So let's go ahead and get started. Um, let's access some prior knowledge. So first of all, we already know that a circle is the set of all points that is equidistant from one central point. That's the technical definition we've talked about. That distance is the radius. And we also know that a perpendicular bisector is the set of all points equidistant from two endpoints of a segment. If you guys recall, we did this in class by, we had two of you holding a string as our endpoints of a segment, and I asked you all to stand so that you were the exact same distance from your classmates, and we wound up forming a line because we were on either side, and that line we defined as the perpendicular bisector. That's all prior knowledge. What we're going to look at today, here's our circle, and perpendicular bisector, that blue line is the line that we formed in class. What we're going to look at today is something called the locus. And what this is technically defined as is a set consisting of all the points and only those points that satisfy specific conditions. So for example, with the circle, if I said, what are all of the points that would be exactly at the end of that leash for the dog, however long that leash was, it would be represented by that circle. The circle would be considered the locus of points around where you were standing, that is this distance of the leash. And then similarly, if I had said for the perpendicular bisector problem, okay, what is the locus of all of the points that are equidistant from those two red endpoints, it would be that perpendicular bisector. Now in this next slide, we're going to define that again. I'm going to go through that again a little bit slower for each of these. We have circle A there, and it's the set of all points that are equidistant from that central point A. But another way of asking that is I could say I want to know what is the locus representing all the points that are the same distance from A, or that are 3 centimeters from A, however I would define that. And we'd say that the circle is the locus of points that are equidistant from point A. If we wanted to include this as coordinate geometry, we could have that at the center at an ordered pair and have you guys figure out what the radius, or give you a radius, and we can write the equation of the circle and say that that equation represents the locus of points that are equidistant from point A. Similarly with our perpendicular bisector example, okay, if I wanted to know the locus of points that are equidistant to both A and B, it would be the locus, the perpendicular bisector represents the locus of points that are equidistant from points A and B. And again, if it was coordinate geometry, we could calculate the slope between A and B, take the perpendicular slope to get the slope for our perpendicular bisector, find the midpoint of A and B. Now we have a point and a slope, and we would get the equation of our line and say that line, or that equation, represents the locus of points that are equidistant from A and B. All right, now those are about as simple as we're going to get. Okay, so there's going to be a 4-step procedure that we're going to look at to find the locus. The first of those 4 steps is going to be to draw the given figure or situation. If I take a step back and I say, what is the locus of center, or the locus of points that are equidistant from point A? Point A was the given. We're going to draw that as our first step. Okay, or what is the locus of all of the points equidistant from A and B? Well, we're going to draw A and B, and that's going to be our given. So draw the situation that's given to you, then start locating points one at a time that satisfy the given conditions. So if I said the points that are 3 centimeters from A, then find one point that's 3 centimeters from A. then find a second point that's 3 centimeters from A, then a third point that's 3 centimeters from A, and a fourth, and a fifth, and a sixth, and if you continue in that pattern, you're going to recognize the circle pretty quickly. Same thing that we did essentially when we were in class with the perpendicular bisector, and all I said was, I want you to stand up and be the exact same distance from your classmates. And you found multiple points that you could do that. By doing that example, you were finding the locus. Okay, so find multiple points and draw them, graph them. Then draw a smooth geometric figure. Smooth geometric figure means draw a line, draw a segment, draw a circle, draw a plane, draw a cylinder, draw a cone, whatever that may be that you have represented by all of the multiple examples that you drew and you came up with, that's the figure we want you to draw. But we're not done there. It is a 4-step procedure for finding locus. We still want you to then also write a description of the locus. Your picture might have a lot going on, and it might not be as easy to locate or see what it is. So I want you to describe it. I want you to say, the locus is the circle around point A with a radius of 3. The locus of points is represented by the perpendicular bisector of the segment formed by A and B. Things like that. All right, so that's our 4-step procedure. We're going to do a few examples together before I have you guys go off on your own. So, first one. What is the locus of all points equidistant from the sides of an angle? Okay. Step 1, draw the given. What have we been given here? Well, what is the locus of all points equidistant from the sides of an angle? So we've been given an angle. So we draw an angle. Any angle. It doesn't have to be acute. It can be an acute angle or a right angle. I drew an acute angle. Okay. Step 2. Find all the points, or as many points as you can, that satisfy that condition. The condition is equidistant from the sides. Remember, what that means is, if I find a point here, for it to be equidistant, that is a perpendicular distance. So those two dashed lines that keep appearing there are perpendicular. That point, as long as those two segments are equal, satisfies the condition. Can we find another point that does it? Sure. I can go closer to the vertex. That would also do it. I could go even closer to the vertex, or further, or in the middle. And what we start to see is the pattern that's developing. I have found multiple points that satisfy this condition. I now see what this pattern is going to be. I can draw a smooth geometric figure as step 3. And it's going to be this ray. That ray is the locus of center. So now I have to write a description of what that means. The locus of all points equidistant from the sides of an angle is the bisector of an angle. So this angle and this angle are going to be congruent, and they are going to be exactly half of the original angle. So step 1, draw the given. Step 2, find multiple points that satisfy the condition. Make sure if you can think of any other points. So if I've found another point over here, well, if these angles, we'll get examples like that. It's not going to necessarily work, but it could. Where it's equidistant to the sides, but the distance is always drawn perpendicular. So it gets a little bit more complex. And believe me, we'll get there with complexity with these. All right, so let's start with this as adding some complexity. Find the locus of all points equidistant from two parallel lines. We have to always assume we are talking about this in a plane, so in 2 dimensions, unless stated. It could state in space or in 3 dimensions. So understanding that there are 2 different answers to this, whether it's in a plane or in space. Okay? So I've already done step 1. I've drawn the given 2 parallel lines. Okay? I'm not going to go through all the process in a plane of, well, this is a point that's equidistant to the 2 lines. This is. All of these are points. So at the end of the day, what have I done? I've drawn this line. Okay, we'll call it line M. And then I'll give it a description. Line M is the locus, and the locus in a plane is the line that is located halfway between and parallel to the original 2 parallel lines. So we can get as detailed as we want in our description there, but it needs to basically state what it is that we have found. Okay. Now, think three-dimensionally here when we're talking about in space. Sure, that line still is equidistant, but what if we stepped out towards you in front of that line, or kept moving backwards behind that line and kept moving back, back, back? That's also going to be equidistant. Essentially, think about taking a piece of paper through your computer screen right now, right where line M is here. All of the points on that paper are going to be equidistant. So we would represent that as a parallelogram, but that's really a plane. So that plane, I named it plane N, is the locus. We go through a description and say that the locus in space is the plane located halfway between the two lines. All right, you guys are going to have a worksheet that's going to have a whole bunch of practice problems on there, and I'm going to post a blank worksheet for you guys to work on, and I'll also post an answer key. I encourage you to try everything without the answer key if you can, and then go and check your answers and make corrections. I definitely will have a Google Meet on this. I think it's something that's important that you have an opportunity to answer questions. That Google Meet session will likely be on either Monday or Tuesday. I haven't necessarily determined that yet, but I will post that on Classroom as well. Good luck with everything, and feel free to send me an email if you have questions.